Hello, good morning, good afternoon, good evening, good day, wherever you are watching my channel. Thank you for taking time out to come to my channel and watching this video. Now in this video, I will be doing more analysis using STATA. This time I will be doing test of differences in STATA. I'll be examining differences in STATA. What I mean by examining differences is I'll be doing various tests that you can do in STATA to test hypotheses, basically for parametric analysis. We're doing Ttest, we do ANOVA, we do ANCOVA, MANOVA, MANCOVA, Posthoc Test, and correlation. These are various analytical approach that you can use to test hypotheses in a research. My name is Peter Daniel. I'm a consultant with Smart Africa R&D Consult Limited. So just like I did in this previous training video, I will first run you through the slides, then I will do hands-on session. Now, the data set used for the analysis are basically hypothetical. The data set used for the analysis in the slides is different from the one I'll be using for the analysis. They were just the one in the slides was just generated for the purpose of building the manual, and also the one for the hands-on session is just generated for the purpose of the hands-on session. So the result may not go the way you may expect it, but the essence of the video is that you know how to do the approach. You know how to run the analysis yourself. So I will take it gradually, take it slowly, and run you through all. I make the video short. If I cannot finish all in this video, I'll do another video to complete it. All right, so let's get into the course immediately. Ttest, ANOVA, ANCOVA, MANCOVA, Posthoc Test. Ttest, ANOVA means analysis of variance. ANCOVA is analysis of covariance. MANOVA is multiple analysis of variance. MANCOVA, multiple analysis of covariance. Then the Posthoc Test and correlation. All right, just before I start the test, this is just like a summary and a guide for you to know why and which to use per time. If you have a dependent variable that is continuous or discrete, that is quantitative data, one dependent variable and one independent variable that is continuous as well, you can do a Ttest. Now later I will show you that there are three types of Ttest. For one-way ANOVA, it means you have one dependent variable that is discrete or continuous and one independent variable that is categorical. It has to be between three category, or two or three category. Of course you can do that, but sometimes when you have two category, you can as well just go back and do a Ttest. Two-way ANOVA is you have one dependent variable that is continuous or discrete, but you have two or three categorical independent variables. ANCOVA, you have one dependent variable that is continuous or discrete, then you have two independent variables. Now these two independent variables, one is continuous while the other one is categorical. Then MANOVA, you have two dependent variables in this case. They are both continuous or discrete. Then you have one, two, or three categorical independent variables. MANCOVA, you have two dependent variable that is continuous or discrete, and one, two, or three independent variable that is either with one or two being continuous, then one more that is categorical. Okay, for a logic, your dependent variable is binary, and you have, of course, multiple independent variable, and it takes all types. OLS, one dependent variable that is discrete or continuous, the multiple independent variable. And for correlation is not here. Okay, let me quickly talk to correlation. Correlation, you have one continuous independent variable and one continuous dependent variable. All right, this is just like a guide in choosing which analytical approach to use. Now, a T-test is a statistical test that can be used to compare the means of two groups. It is often used in hypothesis testing to determine whether a process or treatment actually has an effect on the population of interest, or whether two groups are different from one another. What types of T-tests should I use? And this is the question. Now, if the group comes from a single population, that is measuring before and after an experiment or treatment is performed, a peer T-test is used. You want to compare two groups within the same population, you use a peer T-test. Now, if the groups come from different population, now in this case, you want to test two different species or people from separate cities, you perform a two-sample T-test, or called an independent T-test. That's the groups you are comparing, they are from different population. Now, finally, if you have one group, that's meaning you want to compare the value with a standard value, like comparing the acidity of a liquid to a neutral pH of 7, you perform a one sample T-test. Now, these are the three types of T-tests. So this will guide you to know which one to do per time. Now, one sample T-test. One sample T-test is a sample of what the result is. Now, you pay attention to the codes. These are the codes I will be using to run it on STATA. So, a T-test, this, how old are you guys? Age compared to 5. So, you have the mean age of 45. You want to compare the age of your sample to the mean age of 45. Then the two sample T-test, in this case, this is unpaired. This is independent. Then you have the paired sample T-test, the next one. So I will run this during the hands-on session. Now, okay, you can also do the T-test, independent sample T-test by groups. So probably you want to test effect for male, test the effect for female. All right. Now, to talk to the result, like I want to interpret this table, you pay attention to the far right. You see the T value. This is the T value at minus 9.47. Of course, you take advantage, you ignore the negative sign, you pay attention to the absolute value. And you look at the one in the middle, that's the HA hypothesis. I mean, this is now doubt depends on how you specify your hypothesis, but I'm going to take it that the hypothesis has been specified as how do you call it now? The hypothesis is not one way. It's not one way in the sense that you have not said that the hypothesis, you have not categorically said that one is higher than the other. And you have not, example of what I mean is, you didn't say that age is significantly different from maybe a particular variable. You have put it in a way that it can either be both ways. It's either it is this way or this way. When I remember the actual word, I will tell you. Okay, so we pay attention to the null hypothesis in the middle. That is HA with the result in the middle. So from this, we can see that the T is significant at 1%. And mind you, T values are significant at 10, 5, and 1%. At 10%, it means the T value is above 1.68 but below 1.95, which are the critical values, the absolute value. At 5%, it means the T value is above 1.95 but is below 2.58. Then at 1%, it means it's above 2.58. You can always check your this 4-figure table now. You can always check this table to get these figures I just called out. So that's what we are comparing this T value to. But if you don't want to check your 4-figure tables, you can just pay attention to the probability parameter that is here. We have 0.000. And when we do hands-on session, let's hope that we have various way the result comes out and it's not this smooth, so that you can see the variation. All right, this also is significant at 1%. This is also significant at 1%, giving attention to the t value. So if I'm to interpret this now, I will say this is a t value with age and income, Ttest, to compare age and income. So you can say that, of course, there's significant difference between the age of the respondent and their income. So it's either the age is increasing, the income increase with the age, or vice versa. But however, we can categorically say that yes, given the value of the t statistics, there is significant difference. All right, let me quickly go to ANOVA. Now, ANOVA stands for analysis of variance. Statistical test used to analyze the difference between means of more than two groups. So I say when you have groups that are just two, t statistics can do it. But once it's more than two, you switch to ANOVA. ANOVA will do better. ANOVA is a better analytical tool when you're doing experiment. So ANOVA will give you better analysis when you're doing experiment. All right. So when do I use one-way ANOVA? One-way ANOVA is used when you have collected data from one categorical independent variable and one quantitative independent variable. The independent variable should be at least three levels. Those are three different groups or categories. All right. Then the post-hoc test. Now, post-hoc test is conducted because one-way ANOVA is omnibus test and cannot tell you which specific groups were significantly different from each other. It only tells you that at least two groups are different. The F statistics tells us if there is a need to perform a post-hoc test or not. If the statistics is significant as it is for state and chain, then some post-hoc tests can be done. But where the statistics is not significant, then there's no need to talk about the variable. So what this is just trying to say is that when you do an ANOVA test will tell you the overall effect, overall impact of, let's say, the experiment, overall impact of, let's say, all the addictive you are putting or the treatment you are putting. That's what the ANOVA will tell you. But the post-hoc test will now go further to tell you that, okay, if you have this, if this treatment were done at 25%, 50%, and at 70% inclusion, at what percentage actually was that effect felt? So was it at 50%? Was it at 75%? ANOVA will pull all together and say, okay, the treatment has effect. But the post-hoc test will go further to tell you that no, at 25% there was no effect, but at 50% there was effect. All right. So this sample result of one-way ANOVA. So okay, from here you pay attention to the second table, the F value. Now the F value is not significant. For an F value to be significant, we expect it to be at the least 5 and above. Sometimes, occasionally, when you have 3.9 and above, it may be significant at 10%. But at 5 above, you are sure that it is significant. So we can also see the probability level that is way above the acceptable level. This probability should be maximum of 0.01 or 0.10, that is at 10%. But 0.05 is okay, and 0.01 is okay. All right, that's one way. So now this is the post-hoc test. But this result, since it's not significant, ideally there's no need to do a post-hoc test. All right. Okay. Now two-way ANOVA. A two-way ANOVA compares the main difference between groups that have been split into two independent variables called factors. The primary purpose of a two-way ANOVA is to understand if there is an interaction between two independent variables on the dependent variable. So in this case now, we have more than one independent variable. We have two independent variables. So what that means, for instance, you're having 2 treatments, not 1 treatment. You are giving 2 treatments to a particular dependent variable. And this is sample result of Way Anova. So the result is a little bigger than the other one, and we're still paying attention to the F statistics. So if you look at this now, you see the first side of the table saying the model is significant. But when we come down to look at the particular independent variable, you see that it's the combination of the 2 independent variable, polysorbate and chloroquine, that became significant at this is significant at 5%. The F statistics 2.52 is at 5%, 0.02. All right. Okay, I hope you're understanding. You can always reach out to me. You can always ask me questions. You can always bring your data set for us to do analysis together. I'll be happy to come in to help in your research. All right, so it's the main effect. Okay. Then analysis of covariance. One way ANCOVA, that's analysis of covariance, can be taught as an extension of Way Anova, but it incorporates a covariate. ANCOVA is used to determine whether there is a significant difference between 2 or more independent, unrelated groups on a dependent variable. ANOVA overlooks the difference in the group means. The ANCOVA looks at the difference in the adjusted means. Just like ANCOVA has the additional benefit of allowing you a statistical control for a third variable, sometimes known as a confounding variable, which you believe will affect your result. The third variable that could be confounding your result is called covariate, and you include it in your Way Anova analysis. Now, the ANCOVA, you have the ability to add one continuous variable, that's the covariate, that you feel may have effect on your analysis, not necessarily categorical alone. So you can add a covariate which is a continuous variable. All right, so this is a sample of the results, just like the ANOVA, but the difference is that we have a continuous variable added to it. All right. Now, MANCOVA, MANOVA, multiple analysis of variance, is an extension of univariate analysis of variance. Now, in an ANOVA, we examine the statistical difference in one continuous dependent variable by an independent grouping variable. The MANOVA extends this analysis by taking account multiple continuous dependent variables. And the benefit of this is that you can have more than one dependent variable that are continuous in your model, and the MANOVA will run the analysis. The MANOVA will compare whether or not the newly created combination differ by different groups, level, or independent variable. In this way, the MANOVA essentially tests whether or not the independent grouping variables simultaneously explains a statistically significant amount of variance in the dependent variable. So the benefit here is that you can have 2 dependent variables that are continuous. All right. So now you see from the code, MANOVA, sleeping hours is continuous, body mass index is continuous, while palaxine is the categorical variable. So you want to see if this drug have effect on both sleeping hours and the body mass index. Then you run your MANCOVA. So this gives you 4 tests: the Wilkins lambda, the Pillar's trace, the Lowry Hotelling trace, the row largest root. So you pick depending on what you have, your research protocol, you pick the one that you want. In this test, okay, we can say that, okay, yes, the drugs had effect because the probability, they are all significant at 1%. However, sometimes Wilkins lambda is always sometimes recommended, but of course, whichever way, you will know the statistical protocol you stated in your research. Now, this is the underlying regression that produce that result. You can check the underlying regression that produced that regression. Now the difference between this is that if you're running an OLS or a probit or other OLS model or ML, maximum likelihood models, your dependent variable has to be 1. But with the multiple analysis of variance, you can have 2 dependent variables. This is so interesting, and it's something that you can look into for your analysis. Alright, so this is a two-way MANOVA. That is, you have 2 dependent variables that are continuous and 2 independent variables that are categorical. Of course, the table is bigger compared to the first one. Then we have MANCOVA. Now, this is where we have the covariates. So the MANCOVA analysis of covariance is an extension of the MANOVA, but it incorporates that covariate. That is, you have the ability to have covariate. The one-way MANOVA is used. MANCOVA is to determine whether there is significant difference between the adjusted means of 3 or more independent unrelated groups having control for a continuous covariate. So in this case, you can have one continuous variable in the independent variable, just like we have in the ANCOVA. I'll run the hands-on session so you see how it looks. Now, these are all important for experiments. These are all approaches you use when you're running an experiment. These are all approaches you can use to test for hypotheses. Now, the MANCOVA is how the one-way MANCOVA. This is how the result looks like, and of course, you see we have added how are you here? We have added age, we have added height. Then we have one categorical variable here. You see that? All right. Then, of course, the Posthoc test will now tell you which actually gave the right effect. Now, covariance and correlation, just a slight difference between covariance and correlation. I'm going to talk. Covariance is a measure to indicate the extent to which 2 random variables change in tandem, while correlation is a measure used to represent how strongly 2 random variables are related to each other. Covariance is nothing but a measure of correlation. Correlation refers to the scale form of covariance. Now, I'm going to talk a little about correlation. Correlation is just a test where you use to check the relationship between 2 variables. You do correlation, and depending on how you state your hypothesis, if you have stated your hypothesis by saying there's no significant difference, then you say that you are doing a Ttest, a MANCOVA, a MANOVA, ANOVA, or any of those analysis of variance. But if you have stated your hypothesis by saying there is no significant relationship, now pay attention: significant difference, significant relationship. If you say there's no significant relationship, then you are definitely coming to do a correlation analysis. Or so a correlation analysis will tell you the way these variables are related, and also tell you the strength of the relationship, and it ranges between 1, -1, and +1. While covariance varies from -infinity to +infinity. So this is what the correlation result look like. This is what it looks like. And the correlation, like I said, is for 2 continuous variables, 2 quantitative variables that are continuous or discrete. All right. So this is what the table also looks like. The table looks like. I'll run 1, so we see. Then the chi-square. Chi-square is the chi-square statistic is commonly used for test relationship between categorical variables. Now, the chi-square is useful when your variables, both variables are categorical. In correlation, we are saying the variables are continuous. In chi-square, they are categorical. But in Ttest, we have a mix of continuous and categorical. In ANOVA, we have a mix of continuous and categorical. In MANOVA, the dependent variable is 2. We have 2 dependent variables. So pay attention to this little difference. So the chi-square test for non-parametric analysis that evaluate frequency in a sample and compares those to the expected frequency in population. Now, chi-square for basically for non-parametric analysis. So it means you have to check if your variables are normally distributed or otherwise before you adopt this chi-square goodness of fit test looks at one variable, while chi-square difference of means test looks at two variables. So it depends on which you are doing, like goodness of fit or difference of means. Alright, so this is how the chi-square results looks like. The chi-square, look at that. So it is Pearson chi-square. You see it's significant at 1% when you check the relation, the difference between p-alaxin and chloroquine. Alright, it's another chi-square. Alright, interpretation of key statistics. Okay, I will talk to this and talk to this result later. Let me run the hands. Okay, let me just quickly read this before I go to hands-on session. I don't want the video to be too long. Way Anova, the impact. Okay, so from the result, F statistics is 2.82 and significant at 1% probability level. Hence, we fail. Okay, this is signal at. Okay, F is 2.82, so we fail to accept the null hypothesis. Null hypothesis saying there is no significant difference, so we have to accept the alternative hypothesis stating that there is significant difference. It's as simple as that. All right, thank you. So I'll quickly go to hands-on session. Quickly go to the hands-on session so that okay, let me do this. Quickly go to the hands-on session. Yes, so we can. So this data was hypothetically generated, and is just basically for the purpose of this training. You can always try using your data, and of course ask me question, get an understanding of how it is done, then ask me questions. So gender is categorical here, age is continuous. I also have age that is categorical, young, adult. I hope you can see this clearly. You have experience, you have quinine, it's a drug. So I just generated this. So as I start doing the analysis, I will just try to do some all right, so okay, this fine now. These are all codes. I was trying to clean the data. When I brought it in, it was all figures, so I had to clean the data. All right, so let me quickly go to the first slide. Let me go to. All right, so I have. Okay, so I will take it one by one. All right, so this is Ttest. So let's check. Okay, this is age. Okay, let's do Ttest. So let's say you have stated a hypothesis by saying there's no significant difference between the age of your respondent and the average age in the community. So the question will now be, what's the average age in the community? The average age in the community, you can say the average age in the community is 50. So meanwhile, you have now done an experiment by sampling respondents. You want to compare it with the average age, with the mean age. So the code is here, so I'll just do this Ttest. So age, as the age, I want to compare it with the average age, we say 50. So that's the result. So let's say yes, they're saying that there's significant difference. The t-value is 38. There's negative, but pay attention to the absolute value, and we use the one in the middle. Oh god, I'm forgetting this. Okay, so so the mean of the age of the sample is 29, and is the t-value. So if we want to interpret this, of course we are going to reject the null hypothesis, which state that there is no difference between the age in the sample and that of the population, and accept the alternate hypothesis because from our result there is significant difference. All right, so let me quickly go to the next one. I hope I'm not too fast. All right, I'm enjoying myself. I hope you're enjoying yourself too. All right, so now this is a two sample t-test unpaired. So in this case, I want to test if age, okay, let me, depending on that, I'll check for, let me look at our data. I have age and I have quinine. Okay, so let me test if there's any kind of difference between age and quinine. Okay, let me see that. Oh, okay, age and education. Let's see, age and education. If there's any kind of difference between the age of the people of the respondent and their population. Mind you, the first one we did one sample and a mean. So now I'm going to do age and population, or I'm going to do age and quinine and age and education. I can do that twice. So this unpaired. All right, so Ttest using between age and education. So it's unpaired. Unpaired. Like that's independence now. Independence of the. So let's see. Here's the same kind of difference. Yes, the result is showing this. Say the t value. So it's showing that there's significant difference between the age of this, or the sampling of the sample and their educational level. So you say that as the age increases, they attain more education, or vice versa. And so that's what the result looks like. Okay, I can do that again and say age and quinine. Let's see, paired. This is also significant. Okay, now let's do the same thing, but let it be paired. So I'll just remove the unpaired and make it paired. All right, so you see, so the difference in the technicality is that one is for one is in the same population, while the other one is from different population. And of course, see the t statistics here. This is 44. It's 44. Let me see for the unpaired one is 46. So you see that there's slight difference. All right. So okay, I think, let me see what next here. Okay, I did a t. Okay, paired. I've done this. Okay, then okay, by group. Okay, you can do Ttest. And let it do age and educational level by gender. So I want it to do okay, when you see red, that is okay. I forgot to put my comma. All right. Okay, what's happening here? Okay, educational level, Ttest, age and educational level by gender. Okay, so let me go do this from the other side so that we can see it. Maybe I'm missing one off. So I want to do a paired sample Ttest. Paired sample Ttest. I want to check age. I want to check educational level. I still want the confidence level to be 95, that is 5%. I want to do it by, okay, let it do it by gender. Okay, Okay, so let me check what I made. Oh, okay, I missed. Okay, the approach I used was different. Okay, so this is the right command. By gender, I should sort Ttest. Okay. Now this approach I was using will have been done. Okay, let's no need to bore you with that. But this is just what I want to do. This will have been useful if I do it one after the other. That is, I do it when if is equals to male and if equals to female. All right. Okay. So let's see the results now. So for female, this is the result. The significant age has effect. The significant difference in age and educational level for female. Then also for male, let's see, gender. When gender is male, there's also significant difference. So you can actually do for categorical variable. And if you're interested in just one, that was what I was doing earlier. I was trying to do earlier. Let me go back there and show you that. Now all the commands I was running can be done from here. You can actually come here and click and you get it. Let me do the same thing, but let me not use repeat. Let me use if. So if variable now, if gender equals to 1, right? Okay. No, oh, this is not 1. I picked something else. Sorry, I was supposed to pick 1. That is not 1 I picked. I want us to be fast. I also want you to learn. So let it if, okay, if equals to 1. Yeah, instead of 1, I don't know what this is, like I. Okay, so if it's 1, so it will, so now that means you should know what is 1 here. So 1 is male. This is why I don't like the other approach. It sorts my data set. I don't want it to sort it for me. Now it has sorts my data. All right, but that's fine. So if you don't want your data to be sorted, if you don't want to be rearranged in this way, now I only have male, female, so you will not use that by sort. You don't use that command. It's better you do it this way so that you still have your variables intact the way it is from the original. All right, so I've done for gender. I've done for gender and I have for male now. All right. Okay, so let's continue. ANOVA. Okay, now for ANOVA, I'll do one-way ANOVA. Okay, one-way ANOVA. So ANOVA, I want to test the impact of quinine on age. Sorry, my examples are just for you to see how it's done. So it's just simple one way, age and the dependent variable independent, then you tabulate. That's as simple as that. So I'll come say one way, right? Age, which is a continuous variable, quinine is categorical variable, then I tabulate. It's an option. Tabulate. Enter. Check, compare the result with the other one. See the same table. So the F value is not significant. So it's below this. So we want this to be at least 0.10 at the least. All right. At most, I mean, at most 0.10 for it to be significant. So it's not significant. So we've tested at 25%, 50 and 95%. Okay, let me test that on another variable so we see if we have. Let me test it on experience. is another continuous variable. So let's see. Yeah, beautiful. It's significant now. So we said quinine significance on the experience. Please, this is just for the purpose of this. Don't pay attention. So now we can now do a post hoc test to see at what level it is significant. That's why I wanted to do this. So to do a post hoc test to see if it's significant. Okay, now this command is a little long, but let's do it. Let's see. So I say p pairwise mean age. Now the dependent variable is okay, experience, comma, over the independent variable quinine, close it, then mean compare and being Test, then want to see the effects. Mean compare. What's happened to my command? Maybe I have to go through the long way. Okay, I put R in my turkey. So that's what I want to eat. Alright. So now, wow, this is beautiful. So now, remember, the essence of doing a post hoc test is only valid if your ANOVA is significant. Now, see, the ANOVA is giving us the overall effect of the model that quinine, right, has impact on the experience. Okay, I can replace this with sleeping hours. Let me quickly recode this as sleeping hours. Let me rename. Let me see if I can label this variable sleeping hours. Label, define, experience, let it be sleeping hours. So that probably it makes sense for interpretation. So what's happening? Plenty syntax. Okay, no. Label variable, I mean. Okay, label variable experience. Alright, so I've changed it. Look at my file, right? It's now sleeping hours. I think I can rename, right? Let me see if this works as well. Rename experience. Let me just see if this works. Sleeping hours. Does it work? What's happening? Sleeping hours. Okay, so let me drop that. That can be done, but okay. My time is going. Okay, so let me rerun this to see if I can now have it will come out the way I want it. Okay, yeah, it has come out now. I'm seeing sleeping hours. Yes, so I want to see sleeping hours instead of experience. That's just what I want to do so that I can better talk to it. Alright, okay, it didn't change completely. Okay, so let me call experience sleeping hours. So I want to see if quinine has effect on the sleeping hours. So the first model here is showing me that yes, quinine have impact on the sleeping hours and it's significant at 1%. But remember, this quinine was administered at 25%, at 50%, and at 95%. So now, what the post hoc test does is to tell us which of these really had the impact by checking with a Ttest. So when you check here now, at 50% and at 25%, of course, it was significant. At 95% and 25%, it was significant. At 95% and 50% significant. But when you look at it now critically, you see that it was at 95 and 25 we had the best based on the interaction. Taking the t value and taking the q. So there are instances where you run this and you discover that probably only one combination is significant. So if you're supposed to probably give a recommendation, you say, yes, quinine had impact on the sleeping hours. However, it is a combination at 50%, at 95% or 10%, and 25% that had the real impact on sleeping hours. So that will, of course, help you to make a precise recommendation and help you to save cost. Okay. Two-way ANOVA. Now, I don't want this video to be too long. Let me see what we have. Okay, I will stop this video probably at exactly 1 hour, so that if I don't finish at 1 hour, I'll stop it, then I'll do a follow-up video to complete it. All right. Okay, so let me go to two-way ANOVA. So remember, I will say two-way ANOVA. You have one continuous variable and two independent variable. So we'll say ANOVA. So the code is ANOVA. Now, remember, in one-way ANOVA, we'll just say one way. We didn't even say ANOVA. We just said one way. So now, ANOVA, the dependent variable, let's use this sleeping hours. I think, okay, let me try and rename this so that I can rename it here. Let me name it sleeping hours. Sleeping hours. Okay, that's the problem. It's not near. I can't put space. I think I made a mistake in putting space. All right. Yeah, rename. Yeah, there's no space. The command was correct. There's no space. All right. So ANOVA, let me say sleeping hours. What impacts sleeping hours? So let's say intake of quinine and the age. Yes, let me put this too. Or I can put age category instead of the age as continuous now. Yeah, so enter. Wow. So we see the result. Now let's say the F statistics. Now the model, the overall F statistics is showing that yes, the model is well specified and the two variables had impact on the sleeping hours. But when we come down, we now discover that it's only quinine that has impact on the sleeping hours. So I'm interpreting based on the F. The F of the model is 15.04, which is now 1%. Now quinine, which is 19.78, is in now. So, but age category is now significant. So you see, this impact analysis is showing us that it's actually the drugs that is having an effect on the sleeping hours of the respondents. Okay, let's see, what do we have? Okay, we want to check the main effect. Do we still need to do this? Yeah, we've already, let's leave it at that. Okay, now ANCOVA. Yeah, ANCOVA, remember now we have the ability to add one continuous variable to the dependent variable. So now in this, now I will do the same analysis, but I will now use the continuous variable. So I'll say it's ANOVA. It's still the same command. The difference is now that you're putting a C. Pay attention to the C dot. That C is saying that that's a covariate. So I'll say ANOVA. Now I'll put C dot. Let me use age. Now I'm still using age, but now the age is the continuous variable of age I'm using. Right? Okay, we can even run this ANOVA again by saying, let's do, instead of using age category, let's use education. Oh, education is not synced as well. Alright. Okay, let's use gender. Gender is not synced as well. Alright, so let's arrest my case. Okay, so let me go back here now. Let me do the same sleeping hours, but I want to use one covariate. I'm putting C. Let me use age as a continuous variable. So I can take gender off now. So I have a categorical variable and a continuous variable. So now this is ANCOVA now. Wow, so see the result. Quinine age is not significant, but we see that quinine is significant. All right. Let me see, what do we have in next slide? So this is practically hands-on over this MANCOVA. Okay, let me check. I think I can stop here, right? Then I will now start MANCOVA and the other ones in the next video, so that you can at least even take a rest. All right, so thank you very much for watching. Thank you for your time. Thank you for downloading. Please like, please like, please subscribe, please recommend. I will always be here to dish out videos to help you in your analytical pursuit and also in your research work. And feel free to always reach out to me. If you have a question, you can reach out via my email. That was on the first slides. Let me go back to it. You can reach out smartconsult44@gmail.com. My phone number is also 07035908794, or you can put the +234 7035908794. You can always reach me on WhatsApp. So send me an email. I'll be available to help you in any analytical process you have, be it on STATA, be it on SPSS, be it on eViews, be it on Power BI, and be it on Microsoft Excel. Thank you very much for watching. Please subscribe. Thank you.